All right, welcome to Unit 2. So in this unit, we're going to be taking a look more at modeling distributions of data, and we're also going to be taking a look more closely at our distributions and seeing what other numerical information we can get from our distributions. Okay, specifically, we are going to talk about percentiles. The second thing we're going to take a look at is cumulative relative frequency graphs, or something called OGIVs. We're going to take a look at a position of the data using z-scores. How can we transform data? And we're going to define and describe exactly what a all right, so the first thing we're going to take a look at is percentiles. So once we have our distribution, we often want to describe the location of a value in a distribution and tell what percent of observations are less than it. Now, percentiles in statistics might be different than what you've heard before, but percentiles are specifically the number of observations less than it. In a distribution, percentiles are specific locations. An observation isn't in the 84th percentile, so you'll often hear that. Okay, you're in the 50th percentile, you're in the 60th percentile. In statistics, it's at the 84th percentile. So what does that mean if you're at the 84th percentile? If you are at the 84th percentile, that means that you scored better than 84% of your classmates. 84% of your classmates scored worse than you did. Okay, so it's all of the observations less than that value. The official definition is the pth percentile of a distribution is the value with p% of observations less than it. Okay, so we're going to be using this throughout this entire chapter and basically the rest of the year. So just keep in mind, percentile is always the number of observations less than it. All right, so let's say we're taking a look at scores on an exam. Jenny earned a score of 86 on her test. How did she perform relative to the rest of the class? So we have our distribution. We could do our 5-number summary. We could do our box and whisker plots. This is just adding to finding numerical summaries from our distribution. All right, so how did she perform relative to the rest of the class? Well, here's her score right here, 86. In order to figure out how she performed relative to the rest of the class, we could find the percentile. So if we figure out the percentile, we can figure out how much she did better than the rest of the class, or what percent of students scored less than her. Okay, so how would I do that? Her score was greater than 21 of the 25 observations. So if you counted up all of the scores in red, are the scores less than Jenny's because percentiles are less? Since 21 of the 25 are less, or 84% of the scores are below hers, Jenny is at the 84th percentile in the class scores distribution. Okay, we're going to be using this example later on, so just keep this in mind. But once again, if you're asked to find the percentile, count the observations less than it. 21 out of 25 are less than it, so she is specific at the 84th percentile because 84% scored below her. Okay, so what happens if observations have the same value? That means they're going to be in the same percentile. So you calculate the percent of values in the distribution that are below both values. Okay, so that's a little bit tricky. So you're going to calculate the percent of values below both values because they have the same value, so they're going to be in the same percentile. Okay, so this STEM pot below shows the number of wins for each of the 30 Major League Baseball teams in 2012. Okay, so just once again, notice that we have a key here. Do not forget when you're making your STEM plots to include a key. Okay, what I want you to do, just to get some practice with percentiles, find the percentiles for the following teams. The Minnesota Twins, who won 66 games. The Washington Nationals, who won 98 games. And the Texas Rangers and the Baltimore Orioles, who both won 93 games. So take a minute, pause the recording, try those, making sure that you understand that the percentiles are the values in the distribution below that specific number. And then once you have your answers, check them on the next slide. Okay, so let's take a look, see how you did. So the percentiles, just as a quick note, should always be whole numbers. So please round your answer to the nearest integer if you get a decimal. You won't be asked to round to the nearest integer very often in statistics, but with percentiles, you will want to round to the nearest whole number. Okay, so number one, the Minnesota Twins, who won 66 games, are at the 10th percentile because 3 teams did fewer wins than they did. So 3 out of the 30 had fewer. The Washington Nationals, who won 98 games, are at about the 97th percentile because 29 out of 30 had fewer wins than they did. So if you take a look, they were the highest. Okay, we're not including them in our calculation. So how many teams scored below them? 29 scored below them. Okay, the 2 teams with 93 wins, which were the Texas Rangers and the Baltimore Orioles, are at the 73rd percentile because only 22 of the 30 teams had fewer wins than they did. Okay, so you're going to calculate, you're not going to include either one of the 93, everything below both of the 93s, which there were 22 observations out of the 30. Okay, so just remember, hopefully you have this down by now, that the percentiles are always the number of observations less than them. So think like percentile, there's an L, so less than. So anything to help you remember percentile, less than, okay, with your... All right, so you heard me say this at the very beginning. What is a cumulative relative frequency graph? Well, we talked about a relative frequency graph before. So remember, a relative frequency graph was just your percentiles. What is the percentile, the relative frequency to the entire thing? So now we're just going to talk about a cumulative relative frequency graph. So cumulative, think about what cumulative means. It means you're adding over and over. So a cumulative relative frequency graph, or oftentimes you'll hear them at OGIV, displays the cumulative relative frequency, that's a tongue twister, of each class of a frequency distribution. So what does that mean? Basically, all that means is a cumulative relative frequency graph, okay, shows us the percent of observations that occurred, and basically we're just adding each percentile together to get to 100, which you'll see what that means. So if you take a look, this graph talks about the age at inauguration of the presidents of the United States. Okay, so notice here's your various ages. It's labeled cumulative relative frequency. So what that means is if we take a look between 0 and 45, so if I wanted just the relative frequency, that would be specifically talking about from 40 to 45, what percent of observations are in that class. All right, so here we're just going to estimate maybe about 8%. Okay, what a cumulative relative frequency graph says, okay, when I take a look at the percent of observations from 45 to 50, okay, so here this would have been, let's say, about 8 to 20, so 12% of the observations here. So if this is 8% in your first little segment, 12% in your second segment, what your cumulative relative frequency graph tells you is, okay, at 50, there was a total of 20% of the observations. So it's your 8 plus your 12, which gave us a total of 20% of our observations. Okay, so this graph summarizes the ages of the first 44 presidents when they took office. The next slide, we're going to show specifically how the graph is made. So just take note that the smallest value is 0%, to the highest value, which is 1 or 100%. Okay, so how do we make that graph? All right, so first of all, the graph can be used to describe the position of an individual within a distribution or locate a specific percentile. So we make the cumulative relative frequency graph to show the whole 100% so that we can find a percentile, because remember, a percentile is everything less than it. All right, so here's our frequency table. So between 40 and 44, there were 2 presidents. 45 and 49, there were 7. 50 to 54, there were 13. 55 to 59, 12, so on and so forth. In order to find the relative frequency, remember it's relative to the whole thing, I'm going to take the total in that column and divide it by what I have. So 2 divided by 44, that tells us that there were 4.5% specifically in that first class. In my second class, I had 7 presidents that were 45 to 49, so I take 7 divided by 44. That gives me 15%, or about 16% of the presidents were that age. Okay, so this is just the relative frequency. So what does the cumulative frequency tell me? The cumulative frequency is basically adding up that class and the class before it. All right, so in this case, from 40 to 44, the cumulative frequency was only 2. But from 45 to 49, how many total presidents, the cumulative frequency says, add the class before it plus that one is a total of 9, because 2 plus 7 gives me 9. Okay, so for my 22 between the ages of 50 and 54, cumulative frequency would say everybody in those 3 classes. So I'd add 2 plus 7 plus 13 to give me 22. Okay, so notice how your bars keep getting higher, and we're talking about the ages of the presidents from 65 to 69 are 44. Well, where did the 44 come from? There are a total of 44 presidents. So if we're talking about the cumulative frequency of that specific class and everything before it, okay, it should be your total of what you have, which is 44. So how do you find the cumulative relative frequency? So basically what you're doing is just like the relative frequency, you added up the numbers, the cumulative relative frequency, you're basically adding up the percentages. So you had 4.5%, so to get the second one, okay, we had a total of 9 between the 2 classes. You can either add 4.5 plus 15.9 to get 20.5, or you can say, okay, the cumulative frequency was 9, the cumulative relative frequency is 9 divided by 44. So relative frequency just means percents, okay? So which makes sense when we take a look at this graph, that we can easily find the percentile, because all of these, the cumulative relative frequency positions, tell us what percent of the data is at that point plus everything below it. So if you need a little bit more explanation, go ahead on Blackboard and take a look at the video 2.1 cumulative relative frequency video. All right, so take a minute, see if you can answer this question based on what we just talked about. Go ahead and pause the recording, and then we'll take a look at the answer. So was Barack Obama, who was inaugurated at 47, unusually young? And then estimate, notice, and interpret the 65th percentile of the distribution. So remember, interpret means in context, and you have to explain exactly what 65th percentile means. All right. Did. All right, number 1, we would estimate Barack Obama's inauguration age places him at the 11th cumulative relative frequency mark. Okay, so how did we figure that out? So first, we said he was 47. Let's locate that here. Okay, and then let's go over and see where that is on my cumulative relative frequency. So that's at about 11%. Obviously, this is going to be an estimate. So what does that mean? That means that he's at the 11th percentile of the distribution. What does that mean? That means 11% of all U.S. presidents were younger than Barack Obama when they were inaugurated, and about 89% were older when they were inaugurated. Okay, so how can I estimate and interpret the 65th percentile? All right, so number 1, let's find the 65th percentile. All right, it's right here. Let's go over to my graph. Okay, and then let's go down and see what age that was, age 58. Okay, so now what does that mean to interpret that? Remember that interpreting it means that 65% were below that age. So about 65% of all U.S. presidents were younger than 58 when they took office. So you just don't want to say that 65% of the data was less than 58. That if you give that to a reader, they're not going to know what you're talking about. So specifically, you want to make sure you put that in context. About 65% of the presidents were younger than 58 when they took office. All right, so let's just get a little bit more practice with our cumulative relative frequency graphs. All right, here is a cumulative relative frequency graph showing the distribution of median household incomes for the 50 states and the District of Columbia. So the first question I would like you to answer is A, California with a median household income of 57,445, what is its percentile? B, what's the 20th percentile for this distribution? And then think back to Unit 1, what's another name for this value? And then where is the graph the steepest, and what does this tell us about the distribution? So take a minute, pause the recording, see if you can answer the questions, and then we'll go over the answers on the next slide. I apologize. Also find the IQR for the distribution. Okay. How do I find the IQR? Remember, the IQR is going to be the quartile 1 and quartile 3. So that's the 25th percentile and the 75th percentile. All right, so the 25th percentile, you're going to go to 25. We already said that that was right at 45. What's the 75th percentile? All right, so the 75th percentile, we're going to go up here, is right about, it just depends how you estimate it. Okay. So either can be about 55 or 57,500, and then to find that you're going to subtract the two to get about 12,500. If yours is a little different, that's fine, just based on how you estimated the median household income from the graph. All right, so let's quickly take a look at z-scores. So hopefully you've heard about them. Z-scores are used all over the place. I was even reading an article about a football team. I forget which one it was. I actually think it was the Redskins. And they were discussing how they use z-scores to compare their rankings over the various years. All right, so let's talk about Macy. So Macy is a 3-year-old female, and she's 100 centimeters tall. Brody is her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy, but who's taller relatively speaking? Is Macy a taller 3-year-old, or is Brody a taller 12-year-old? According to the Centers for Disease and Control Prevention, the heights of 3-year-old females have a mean of 94.5 and a standard deviation of 4. So remember, standard deviation is your average distance from the mean. The mean height for 12-year-olds is 149 centimeters with a standard deviation of 8, relatively speaking. Ooh, let's take a look at that. That's interesting, though. Clearly, 3-year-olds have much less variability than 12-year-olds. Okay, so z-scores, what they'll do is they'll tell us who's taller, relatively speaking. Okay, so what exactly does a z-score tell us? A z-score gives us another way to measure the position of a specific point in our distribution. So our percentiles told us what percent of the distributions were below that specific value. A z-score is going to tell us how many standard deviations from the mean in observation falls, and in what direction. Is it above the mean or below the mean? All right, so you've seen z-scores before, hopefully. So if x is an observation from a distribution that has a known mean and standard deviation. So to find a z-score, we have to know what the mean and standard deviation is. The standardized value of x. So standardized means that when I find a z-score, it's in standard units, and I can compare it to anything else. So basically what standardized means is there are no units on my z-scores. So a z-score is, okay, let's take my observation, let's subtract the mean from it, and that tells us exactly how far it is from the mean, but then let's divide by the standard deviation. Let's divide by the average distance from the mean. That will give us our z-score. Okay, by standardizing an observation, we change the value from the original units to the standard deviation unit. So the standard deviation's in the denominator, that's your new unit. Okay, so z-scores don't ever have meters, centimeters, standard deviation does, but not your z-score. It's not measured in the same units as the variable. It is measured in standard deviations. How far are you from the mean specifically? If your standard deviation is positive, it's above. Okay, so a z-score tells us how. Okay, so we can also use z-scores to compare the position of individuals in different distributions. So when we say different distributions, they can have different units. They can be completely different. One's SATs, one's ACTs, talking about heights. The reason that we can do that is whenever we standardize our scores, we're giving it a standard unit of measure, which means they have the exact same units, and those units are standard deviation. Okay, so number one, when we talked about Jenny, first we knew she earned a score of 86 on her statistics test, where the class mean was 80 and the standard deviation was 6.07. She earned a score of 82 on her chemistry test. The chemistry scores had a fairly symmetric distribution with a mean of 76 and standard deviation of 4. Now, why would I say fairly symmetric? Remember that we only use the mean and standard deviation when we're specifically talking about approximately symmetric distributions. Okay, you cannot use the mean and standard deviation if they're not symmetric. So in which test did she perform better relative to the rest of her class? Okay, so we can figure out in standard deviations how far above or below her class she did. So let's do statistics. We already did that one. We said her test score 86 minus the average 80 divided by the standard deviations. So her z-score for statistics was 0.99. So she scored 0.99 or about 1 standard deviation above the mean in statistics. How did she do in chemistry? Okay, so we take her chemistry score minus the class average divided by your standard deviations. That gives us a score of 1.5. So that means she did 1.5 standard deviations above the mean in chemistry. Oh, so which one's actually better? She actually did better in chemistry even though she has a lower score. All right, because she was further above the mean. So she did better in relative comparison to the rest of her class. So Jenny scored better in chemistry in relation to her peers since she was higher above the mean in chemistry than in statistics. Okay, and I'm going to go over this on the next slide, but a key thing with z-scores is you have to show your work. Okay, I know that this is very easy to do on your calculator, but you will not earn credit on the AP exam. Okay, so let's answer the question. Macy and Brody, so who was taller? So they're 3-year-olds and 12-year-olds. They're really hard to compare their height, but since we have z-scores, we can say who's taller on average. So if we take Macy's z-score, her height 100 centimeters minus the 94.5 divided by the standard deviation, since it's positive, we know she was 1.375 standard deviations above the mean. Brody's z-score, okay, he was 158 centimeters, and we could have done this in inches. It wouldn't have mattered because in the end, it just ends up as z-scores minus the average height divided by the standard deviation. So 1.125 standard deviations. Who do you think's taller? Okay, Macy is taller in relation to Brody since she's 1.375 standard deviations above the mean versus Brody, who's only 1.125 standard deviations above the mean. So she's taller in relation to her peers than Brody is. Okay, so why do we standardize the scores? The whole point of standardizing the scores is so that we can compare individuals from different distributions and different scales. This is how colleges compare ACTs and SAT scores, which are reported differently. They standardize the scores and then they make the comparison. I was always curious how they did that. Okay, when I was in high school, why do some accept ACTs, some accept SATs, and some accept both? How can they make that comparison? Easy, using z-scores. So z-scores allow us to give meaning to our numbers that we collect and compare them to each other. It's like a common yardstick for all types of data. So if I wanted to compare the average height in New Zealand using centimeters versus the average height in the United States using inches, we could compare them using z-scores because they'd have a standard unit of standard deviations. So what else are z-scores used for? Remember getting your height and weight as a child at the doctor's? Guess what? When they looked at those percentile ranks, they would use cumulative relative frequency graphs. Okay, we also use it to test for defects in merchandise. Okay, what else is important about z-scores? I'm taking a whole slide to say this, so it's really important, okay? For z-scores, you have to show the work, okay? Do the calculation on the calculator, that's fine, but do not ever report a z-score without showing the plug into the formula. Make sure you label it as z equals. Don't just write your observation minus your mean divided by the standard deviation. You must label it as z equals, okay? Because later on, not everything's going to be z-scores, so include that label. All right, so here's a good example of how it should look like if you want to put that in your notes. Your z-score of chemistry equals the observation minus the mean divided by the standard deviation, and then as part of your answer, z equals, okay? Don't just write equals 1.5. Well, what is 1.5? It's your z-score. We know it's in standard units according to z-scores. All right, so last thing in this section we're going to take a look at is transforming data. So what transforming data does is it converts the original observations from the original units of measure to another scale. So what do transformations do? They can affect the shape, the center, and the spread of a distribution. All right, so let's just see what happens if I add or subtract a constant. Let's say I'm going to add the same number, either positive, 0, or negative, to each observation. What it does, if I'm going to add some number a to the measure of center and location, the mean, the median, the quartiles, and the percentiles. So if I add a number to every single solitary observation in my data, it's going to make the center increase, it's going to make the mean increase because I'm moving it along a scale, the median increase, the quartiles, and the percentiles. However, it does not change the shape of the distribution or the measures of spread, the range, the IQR, or the standard deviation. And we'll go over what that looks like in a minute. By adding or subtracting a constant from each value, you're essentially moving the data right and left along the number line. So if we're moving it right and left, that makes sense that the mean's going to change, the median's going to change, the quartiles and the percentiles. But if I'm physically just taking my graph and moving it right or moving it left, it's not going to change the shape, okay? It's not going to change the range, all right? The range is just from the highest to the lowest. If I move the highest and lowest along the graph, there's still the same distance between the highest and the lowest, along with the IQR and the standard deviation. Okay, so let's just take a minute and see what happens when we transform our data. So here is a graph and a table of summary statistics for a sample of 30 test scores. So the maximum of your possible test scores was 50. Let's just take a quick look at some of the summary statistics. We have a total of 30 values here. Our mean was 35.8, okay, so right about there. Our standard is moving it over 5. We're physically taking it and picking it up and moving it over 5. The spread and the center of the distribution aren't changing. All right, so let's just take a look at our data for a second. Our mean did increase by 5. Why did our mean increase by 5? Because if I added 5 to each of my data points, then when I'm averaging it, I'm averaging 5 more to each of my data points. So I just added 5. The standard deviation didn't change because that measures our spread of our data. Our data isn't any more or less spread out when I physically took it and moved it over 5 on the number line. The minimum, the quartile 1, the median, the quartile 3, and the max are all going to increase by 5 because I took them and I moved them over 5 points. However, notice your IQR and your range, all right, they are also measures of spread. They did not change because they did not change because we moved my graph over, but I didn't change how spread out it was. Just my summary statistics, okay, your 5-number summary, and your mean changed. Your IQR, your range, and your standard deviation did not change at all. Right? So basically, the effect of adding or subtracting a constant is it's going to add or subtract that value to your mean, your min, your quartile 1, your median, your quartile 3, and your max, but it's not going to change your spread. Okay, so let's take a look at the next type of transformation. All right, so what exactly happens when we multiply or divide all our data by our constant? Suppose that the teacher in the previous example wanted to convert the original test scores to percents. So because the test was out of 50, he should multiply each score by 2 to make them out of 100. Here are the graphs and summary statistics for the original scores and the doubled scores. All right, so if we take a look at this, here's our first score. All right, how does that change when we multiply each score by 2? All right, so let's take a look at our summary statistics. All right, number 1, we actually still only have 30 data points, but take a look at our mean. Our mean was 35.8, but since I multiplied each value by 2, that means it's twice as large. So when you're averaging them all together, you're going to average something twice as large. So that means that the mean is also going to be twice as large. All right, take a look at the standard deviation. The standard deviation in the first one, 8.17, the second one is 16.34. That standard deviation is actually twice as large. So in this case, the spread did change. All right, if you take a look at the first one, look at the spread of your data. All right, you originally had your minimum was 12. Your new minimum is now 24. Okay, so our minimums were 12 and 24, and our maximums are 48 and 96. All right, so our range actually changed a lot. Our range went from 36 to 72. That also got multiplied by 2. Let's take a look at all of our summary statistics. If you notice, the minimum, the quartile, the medium, quartile 3, maximum, the IQR, and the range all got multiplied by 2. So this is different than when you're physically just picking it up and moving it over. When you multiply everything by 2, you're not just picking it up and moving it, you're actually changing the shape of what it looks like. All right, so from the graphs and the summary statistics, we can see that the measures of center, the location, and the spread have all doubled, just like all of our individual observations. But even though the distribution is more spread out, the shape hasn't changed. It's still skewed to the left with a few clusters and gaps. All right, so the shape doesn't change, but the spread does. All right, we still have a long left tail, still skewed to the left. All right, so this is just, I thought, a funny example of describing density curves. So just take a minute and read the comic. Maybe you'll have a little laugh to yourself. All right, so just a quick summary. Our measures of center and spread apply to density curves as well as actual sets of observations. So you might ask yourself, what is a density curve? Well, you've seen a bell curve before, so a density curve is very similar to the bell curve. So how can we distinguish between the median and the mean of a density curve? The median of the density curve is the equal areas point. So remember, the median on your number line was half the points were above, half the points were below. So a density curve is like a bell curve. The median is going to be the middle, where half the area is equal above and half the area is equal to it below. The mean of a density curve, or what I said sort of looks like a bell curve, is the balance point at which the curve would balance if it was made of solid material. So it's kind of, your mean is like your teeter-totter. Okay, so your median, think middle. It has to be the same area on both sides. The mean isn't necessarily where in the middle, it's the average. So the mean is going to be where your teeter-totter balances. The median and the mean are the same for a symmetric density curve. So that means if we had something that was perfectly symmetric, a perfect bell curve, all right, the mean and median would be exactly the same, and they would both lie at the center of the curve. The mean of a skewed curve, remember, is pulled away from the median in the direction of the tail. So if we have a long left tail, the mean is going to be pulled towards that tail. All right, so here's a density curve. Literally, a density curve is just sort of like a normal curve. Okay, we're going to be talking about normal curves later, but it looks like a bell curve, or it can be one that's skewed. So just the general idea, the mean and the median, if you take a look, this is where it's balancing on the teeter-totter, and for the median, there's the same area to the left of the green as the right of the green. However, in your second one, notice this is skewed to the right. The median, all right, it's harder to figure out where that is, but it's closer to where most of the data lies. The area to the left of that green curve is equal to the area to the right, versus the mean, the areas aren't equal, but it's where your curve would balance. Okay, so a teeter-totter where it would be, to balance. All right, so just as a summary, we learned that there are two ways of describing an individual's location within a distribution, our percentile rank and our z-score. A cumulative relative frequency graph allows us to examine location within a distribution. It's common to transform data, that's when we're adding or multiplying, especially when changing units of measurement. Transforming data can affect the shape, the center, and the spread. Just remember, adding and subtracting only affects the center, and multiplication division will also affect the spread.